Hey everyone, just a classical question before we start. Can you all hear us? Let us know in the comments. So I'll be just waiting for the first one to confirm we're live. I didn't see any comments, so just to confirm if you hear us again. Okay, perfect. Great. I'm Jan. I'm one of the founders of Uplover. According to Financial Times, one of the fastest growing software development companies in Europe. Our core specialization is health tech, since our mission is to build meaningful software. Our DNA in general is working on technologies for the most dynamic and recognizable brands on the domestic market and worldwide. And one of our core values is to share knowledge. Therefore, today, welcome on our webinar, AI Hot Topics, Revolutionizing Healthcare with Artificial Intelligence. Of course, this is a series, and for those of you who did not see the previous ones about machine learning, webinars about machine learning, feel free to visit our YouTube channel where they are published. We have Philip with us, our machine learning lead, who will tell you more about that topic. So without any further ado, Philip, the floor is yours. And last comment, you obviously feel free to ask questions. I'll read them over closer to the end of the webinar in order to just make it in time that we promised. Philip, come on, let's go.
Okay, thank you. Hello, everyone. Once again, I'm Philip. I'm lead machine learning engineer at Uplover. And today I would like to talk to you about AI hot topics in health tech, or how to revolutionize healthcare with machine learning and artificial intelligence. And without further ado, if I could only, yes, thank you. And let's start with our agenda for today. So we'll start by talking about machine learning and AI, the ever-changing field of ideas. And we'll try to answer why now is the time for it, and how to get the most out of it. Then we'll move to the AI revolution in health tech specifically, and we'll discuss some ongoing projects, including clinical decision support systems, medical imaging, telehealth, preventive and personalized healthcare, and to top it all out, AI regulations. And after that, we'll try to see what lies ahead. So we'll talk about BCIs, brain-computer interfaces, quantum-enhanced machine learning, and general AI. And after that, we'll wrap it all up with some conclusions. So with that out of the way, let us begin. So, machine learning has been with us in one form or another for a longer time than we may suspect. The first theoretical works concerning self-learning machines are almost as old as the idea of computers themselves, and the mathematical tools and algorithms are even older. But in its current form, machine learning is a rather new development, seeing a great boom in the last few years. And we constantly see new publications and new architectures being revealed. New models performing more and more surprising tasks. You may ask yourselves, what caused this? Why now we see another resurgence of machine learning, and it seems that this time it's here for good? Well, there are a few key changes that happen alongside each other, making all this possible. Mainly, the emergence of large data warehouses and means of consistently obtaining and storing vast amounts of data for those warehouses. And the second one, the exponential growth in computing power that we've seen a few years ago. Those two factors removed the obstacles for implementing years and years of theoretical work that seemed unpractical to that point. And with that, we've experienced a real snowball effect. As we implemented our ideas, we were able in turn to use them to generate even more data, optimize our processes, and discover new opportunities for improvements. And previous advancements in machine learning became stepping stones for next ones. Sometimes older models became building blocks for the new ones, resulting in even more powerful solutions. And all this, combined with the rising need for automation and digitization, created a perfect storm for advanced AI and machine learning solutions. But with all those changes and advancements, there is an important question to ask. How to join in on the AI craze? Is it too late? Where even to begin? Well, worry not, as there are plenty of ways to implement machine learning, and the barrier is not nearly as impenetrable as you may think. First off, not all machine learning models and techniques require an enormous infrastructure. Sometimes a simple model and a modest database is a perfect start. There are tools applicable for every stage of technical readiness, and the only problem here is to choose an appropriate one. What is more, most machine learning solutions are scalable, meaning that if you start with a simple model, there is nothing stopping you from scaling it horizontally to be able to handle larger data flows or swapping it for a more complex one entirely. The key here is to plan for this in advance and to develop a modular system, as even a small machine learning module can be a good starting point, and as you gather more and more data, you can then train a more sophisticated model. And this mirrors to an extent the process in which some of those solutions were first developed. And finally, even if you face a problem that can be easily solved by a small and robust system, there are plenty out-of-the-box solutions available. And be it pre-trained models ready for fine-tuning and development, or entire modules that you can simply access through their APIs. And the crucial part here, and the only limiting factor really, is proper understanding of the problem you're trying to solve with the machine learning and identifying what resources are realistically available. After all, the better you know the problem, the better you can model it, and that is the core goal of machine learning. This is particularly important when it comes to specific data formats and its characteristics. Some methods can be better suited for them, some less so. And let's not forget about the second part, the available resources. You may design a perfect system, but if you do not have the technical readiness or the means to gather the required data, it won't be able to get off the ground, really. And both of those parts need to be kept in mind to choose a perfect solution. With all that said, what are those big and revolutionary technologies I've been hinting at? What is currently happening in regards to machine learning, especially in health tech? Well, turns out that quite a lot. Since we not only see a lot of new conceptual ideas, but even actual systems being developed and deployed. Even in the most rigorous environments like hospitals and medical practitioners' work in general. And I'd like to talk with you a bit about some of those solutions, mainly clinical decision support systems, medical imaging, telehealth, and preventive and personalized healthcare. In all of which we see great breakthroughs due to the application of AI. And let's start with clinical decision support systems. So any applications of AI in support of medical personnel, helping them sift through the numerous data and find underlying connections in them. And the final decision still belongs to them, to the medical personnel, but they can make it depending on the use case faster or based on more information that is not so easily available without the system. And machine learning offers here an unique opportunity for dealing with amounts of data not humanly possible to parse in a viable time and presenting them in a digestible form. A rapport, a set of alerts for key points, etc. And those systems offer a great potential, but require a high level of care when implementing them. The key here is to carefully design the system to minimize any chance of false negatives. Since in health tech, a cost of any missed cases is much steeper than usually. After all, we risk less by flagging some cases as potentially requiring care, only to find out that they don't. A worst case scenario here, we get a less efficient system, but still more efficient than diagnosing everyone by hand. And on the other hand, missing harmful symptoms may result in delayed care, which is not acceptable really for a system of this sort. And keeping all that in mind, let's take a look at few applications of such systems. First one is a solution developed by an American startup that aims to measure their patient general health as an index, using multiple machine learning tools and data sources. And this complex system is not only out of the testing phase, but already being used in around 80 hospitals in according to their website. And another promising example is a solution for predictive detection of cardiac arrest in patients, developed by University of Chicago. Trained on historical electronic health register data, this system promises to be able to predict which patients are at risk of heart failures ahead of time, enabling personnel to be ready for such an eventuality and either prevent it or be there on time when it happens. The system was recently acquired for commercial use, and we may soon see it in hospitals in USA. So stay tuned. And in the same vein, another predictive assessment is being developed at Duke Health. This one concerning sepsis risk. And the system is currently being licensed, and as with previous one, awaits introducing to a production scenario. But moving to a different application, another academic team is currently working with some initial successes on a length of stay prediction algorithm. And the goal here is to provide administrative staff of hospitals and other facilities with rough predictions to help them in cost management and providing necessary supplies. And this solution is still in the testing phase, but recently received a lot of funding, so we might see a breakthrough. And moving to machine vision, which is a widely applied tool, so no wonder that it found its way in health tech, and I think it's here to stay. There has been many studies and proposed systems focusing on using machine learning tools to improve readability of medical scans and images, assist in classifying them, and even dedicated detection tools for specific use cases. And just as with clinical decision support systems, the goal here is to present the medical staff with new tools and new angles of analysis, not to replace them. In essence, we are providing the second pair of eyes, specialized in picking up subtle cues, working in tandem with the medical staff. And there are plenty theoretical solutions implementing machine vision in medical imaging, from RTG images to MRI scans, but some not so obvious and standard applications are also possible. Using machine vision, we can try to interpret even standard images, not usually categorized as medical imaging problems. For example, even photos of patient skin or other areas of body can be processed by AI to identify and detect changes or pathologies that we are looking for. And the barrier we are currently trying to bridge is practical applicability, though. Many of those solutions, when tested in practical situations, struggle. And the problem may stem from the datasets used in those studies. Usually, those are biased in one way or another. For example, underrepresenting healthy individuals. Those issues, while fine for a proof of concept solutions, should be resolved before such systems can be deployed without extensive supervision. But even with those issues, such as they are, there are many promising systems. For example, there are extensive studies and many publications concerning cancer detection. And depending on the use case, those studies present accuracy as high as 95 to 98%. And supported with other types of data, such detectors may be perfect form of initial screening, performed without the need for long consultations with specialists, saving time. Another big application of machine learning emerged alongside with the COVID-19 pandemic. We've seen numerous studies using many forms of data, including medical imaging data, like chest X-rays images, to help with early detection and then recovery from COVID-19. And this approach seems to be most helpful in detecting pathologies like microdamage to the lung structure or complications like pneumonia at an early stage. And in the same vein, unlike the last two examples, machine learning has been proposed as a solution for bone fracture severity and malignancy classification. Such tools, as before, serve mainly to assess the risk and detect potentially dangerous cases at the earliest possible stage. And the last example is not a theoretical one, but a working prototype from a Bulgarian startup based on thermal body imaging. And using complex machine vision solutions, it assesses those scans, looking for any abnormalities connected to cardiovascular system and possible inflammations or oncological anomalies. If the system proves itself in the field, it can be a giant step towards developing a complex medical early detection system. Moving to more common and everyday usage, available for everyone, personalized healthcare is, in principle, very similar to a clinical system we discussed at the beginning, but adapted for everyday use. We focus here on your day-to-day life, monitoring and managing it, on your habits, and early signs of possible problems. Those systems usually rely on less specialized and what follows more common data sources. So any smartbands, your phone, maybe simple detectors and sensors that you can have in your home or that you can bring with you when you're out. And those data, surprisingly, can give us a lot of insight and in turn allow us to provide everyday personalized care for our users. Even a simple questionnaire filled every day can help in making useful suggestions and improving your day-to-day routine. Another big advantage of such systems is personalization. As we mostly think here of apps in your smart devices, phones most likely, we can provide a much higher level of personalization and adaptation. Models deployed in such a way can learn yours and only yours data and can be fine-tuned for your maximal benefit. The only caveat here is to remember that such machine learning model still need to preserve a baseline truth, medical truth, and that personalization is only beneficial up to a point. After all, we don't want our systems to model anomalies or harmful behavior, but rather identify them as such and help users to maintain a healthy optimum. And a perfect example, and widely explored to boot, would be a heart rate monitor system. This month, a team of researchers from HIMSS, financed by Pfizer, presented a complex solution catching the essence of such tools. And the proposed solution gathered information about user day-to-day heart rate and activity level. And using machine learning tools tries to identify any abnormalities in user heart rate. If any are detected, the user is notified and then can use the interface to consult the medical specialist or make an appointment. Another tool, this one already FDA approved and commercially available, is a dedicated smart band detecting possible epileptic seizures. Developed by an USA-based company, the device monitors patient electrodermal activity, their temperature, and combines that information with accelerometer and gyroscope data. If a possibility of a seizure is identified, the designated caregiver is notified. And similarly, there are a few publications exploring possibilities of a device dedicated for older people, monitoring their activity level, and based on that, informing about the sudden and abnormal drop-offs, or even physical falls detected using, again, accelerometer and gyroscope data. And such monitoring tools offer a unique form of constant care. And the last application in personalized healthcare I would like to talk about is stress and emotion detection, using wearable sensors and smartbands. As stress is one of our major concerns and negatively impacts our health, no wonder that many researchers explore such possibilities using wearable devices. Those attempts, albeit promising, are still at an experimental phase, but soon may become a useful addition to our everyday life. And moving to another segment, telehealth, as a segment, of course, seems to be an answer to a growing demand for universal and widely available medical care. The amount of people in need of medical consultations is constantly growing, but the limited number of available medical practitioners is not always able to handle it. This problem is perfectly solved by introducing advanced machine learning tools, some similar to solutions described previously, and making them available to patients in need, or using them to handle at least part of the inflowing patients. And natural solutions that come to mind here are specialized chatbots performing medical screening of patients and remotely available diagnostic tools for the patients. And it just so happens that the majority of machine learning applied in telehealth boils down to exactly such systems. For example, an Australian startup is developing right now an advanced teledentistry tool. And the idea here is to allow initial patient screening by remotely monitoring their oral health and providing them with approximate dental health score, and then recommendation to consult the specialist if it is low enough. This is achieved by analyzing photos of user mouths taken with their smartphones according to the instructions. And using machine vision tools and other machine learning techniques, the project claims to be able to roughly assess general dental health of patients and so better manage when the patient needs to show up for the in-person checkup. Another example is a promising series of publications applying large language models for initial screening and triaging patients. And there are many proposed applications spanning from specialize in one type of symptoms, ophthalmic, cardiac, respiratory, to more general ones, focusing more on patient interview and screening rather than pure triage. And the results vary from task to task and from publication to publication. But they are consistently promising, around 70 to 90% of accurate patient assessment, which is more often than not scoring on par or higher than medical practitioners. And although impressive, those results need to be taken with a grain of salt. As far as I know, no working prototype has been yet tested in a real scenario. More immediately promising are chatbots performing initial patient interviews only, gathering data for real medical practitioners. We've already seen classic chatbots being used successfully in this way, and applying large language models for this task seems only to improve their performance by providing more adaptability and flexibility in responses. And to wrap up this segment, let's talk about AI and regulations, as this is especially important when it comes to health tech systems. As it is with all revolutionary technologies, our legislations and safety measures sometimes struggle to accommodate all the coming changes. And we've seen it with the internet, for example. After a long Wild West period, sites with no moderation, no universal standards or templates, and general whatever happens approach, came a sanitization and codification phase. And as of now, it is still happening, albeit slower, as most rough edges have been already smoothed out. And the same goes for AI and machine learning solutions. And as they most often do not handle critical data and important processes, the rule-setting phase is even more crucial, especially in health tech, where sometimes well-being of our users, patients really, is at stake. And it is also a breaking point for many promising projects. They may reach an impressive level of accuracy, but are not proved against those edge cases, resulting in potentially fatal system behavior. Luckily, we already have some regulations in place, and others are being actively defined. First and foremost, the already existing ones apply. So GDPR for Europe and HIPAA for USA. Those alone define rather sharply what our approach to data in machine learning systems should be. Our main focus here should be providing safety for any personal info we use at any stage of our projects, especially the one that falls under the label of medical records, be it heart rate recordings, medical images, or history of illnesses. So not only production-ready machine learning models, but also during our initial phase of testing and exploration, which is often forgotten, we need to keep track of that data. And moving to more machine learning specific regulations, just a year ago, AAMI has published a report and set of guidances concerning the rapidly emerging use of AI in healthcare. It focuses on lessons learned from usage of AI in other industries and defines a set of crucial areas for any machine learning system: data management, model and data bias, and our trust in technology. A big focus here is to not only develop a solution that returns good metrics when tested, but to understand it and to understand why it returns what it returns. Since not always a higher metric equals a better performance in the field. There's also a lot of independent grassroots movements of machine learning engineers and specialists trying to publish sets of good practices. Those are, in essence, very similar to the ideas presented in AAMI report, focusing on understanding your technology, understanding the problem and the data you're trying to model, but also extend to good practices when it comes to developing those models. And hopefully, with time, we'll see a more unified and coherent set of principles set for machine learning and AI. But as of now, we are on a good road to achieve that. So, we talked about what is happening right now and in the near future. But what is yet to come? What we may see on the horizon when we try to look even further? Well, speculations are not an easy task. But there are some really promising trends emerging right now that with proper backup and research can lead to really big changes, and I think that it is worth to keep track of them. Not only from the business standpoint, but simply due to our sheer curiosity, really. And the three big things on the horizon, in my opinion, are brain-computer interfaces, quantum-enhanced machine learning, and general-purpose AI. And starting with a topic close to my heart, BCI, or brain-computer interfaces in full, can be defined as any form of a system that allows us to communicate freely with the computer without the use of any external methods such as hands or any other movements. And BCIs are closely connected to HealthTech and MedTech and find their roots in medical research of brain activity. They may sound exotic, but a lot of research is being conducted and connected right now with a varying degree of success. As with any technology, there are, of course, various approaches, from simple and straightforward to more complex. But most of them relies on some form of machine learning to interpret recorded brain activity. As for the recording itself, the most straightforward and safest way is to record brain activity as you would during an EEG and process the resulting signal to classify them. And depending on the detected patterns, a system may perform some actions. You move a pointer on the screen, activate something, or move a robotic arm. And BCIs, even in its simplest described above form, offer a unique opportunity. Not only for direct and hopefully faster communication with our computer systems, but what is even more promising and exciting, for physically impaired people to interact with the environment. The main obstacle on the road to a commercially viable BCI system, even a simple one, well, it's the signal itself. Even the simplest approaches face problems such as high noise to signal ratio in our brain recordings. What is more, developing an universal system is an even harder task, as brain activity patterns vary from person to person. And each new user needs to not only train himself on how to use the system, but also the system needs to be trained to recognize hers or his particular brain activity patterns. And developing an universal system resolving this issue I described would be a real milestone in the BCI research. And I think it is worth to keep an eye on the development of BCI systems, as they offer a tantalizing possibility for us all. And another, probably even more theoretical possibility than BCIs for now, is an entire new approach to machine learning, known as quantum-enhanced machine learning. And the name says it all. Quantum computing and machine learning. Two hot buzzwords of the IT world together. And as wild as it may seem, we are currently observing the first steps of this discipline. Even though first quantum computers are still in the testing phase and not available apart from a few research centers, some theoretical work is already being done to harness the possibilities quantum computing brings to machine learning. We already see first environments running on standard computers and operating at normal speeds, but simulating quantum effects, enabling us to test some of those theories. And this in turn resulted in the first experimental quantum machine learning libraries and modules. It's still only an experimental phase, though, almost theoretical, but the first steps are being made. But what machine learning stands to gain from quantum computing? Well, apart from the proposed increase in computation speed, the giant one, resulting from the usage of qubits, the quantum bits, that allow the computer to perform much more operations at once. But not only that, but qubits exhibit two main properties: quantum superposition, or in other words, ability to remain in multiple states at once, and entanglement, quantum entanglement, or in other words, a specific type of connection allowing for modifying the state of two qubits by interacting only with one of them. And those two properties open up new limitless possibilities for dedicated machine learning architectures and models, relying not only on the speed, but also those special properties. Sadly, all those possibilities won't be fully realized until we operate only in simulated environments, as good as they may be. Only once we see a higher availability of quantum computers, some of us will be able to test those theoretical and simulated models to see if everything works as it is assumed it would. Until then, we may still plan, test, and speculate, but we won't be sure if quantum machine learning will really surpass our current state of technology. And to wrap it all up, let's talk for a bit about the big and scary one, the general purpose AI, the one we think when we see AI in science fiction. The autonomous, capable of performing multiple unrelated tasks and possessing its own volition, general AI type. In short, a perfect AI mimicking our or surpassing our own capabilities. And although it's probably still a distant thought, and as far as we know, nobody really observed AI expressing a clear sign of sentience or volition, we see it being talked about more and more in media, and some speculate that we may even see it in our lifetimes. Such an AI would be a great blessing. Being able to operate autonomous, be it as an operating system behind a normal machine, or even as human-like robots. Depending on its form, it could easily perform tasks that are extremely dangerous or even impossible for us. Think, for example, about rescue operations in harsh environments or long independent missions. All those situations that require independent thought and decision making. But those exact features of general AI are the most contentious ones. It's a scary thought on the surface. We fear what the AI might do. We fear that it may surpass us, replace us. We worry about such questions as its sentience and general morality of interacting with such an AI. And those speculations are, to an extent, mirroring our own history, development, and experience. Not to say that we shouldn't think about such things, but we need to keep in mind that AI itself won't be capable of feeling, won't become jealous, won't set its own goals, as long as we won't equip it with the ability to do so. A simple principle applies here, as with any tool. It may be dangerous, but only in the wrong hands. And to leave you with a bit of speculations, as we still don't see a clear way for achieving such an AI, there has been many ideas. Some still believe that it is only a matter of scale, and with bigger and bigger neural nets, we may simply see such a thing emerging on its own. Well, I personally tend to believe that a proper direction would be to mimic our own brain and try to connect multiple smaller models or nets, some dedicated to specific tasks like vision, hearing, speech, memory, and some general. Some of the newest experiments and research are going with exactly that idea, simulating human neocortex, but as far as I know, no breakthroughs has been announced yet. Whatever the way to achieving all that may be, we may see general AI sooner than we may think. So, to summarize all that in a few key points, there is no better time than now to join in on the new AI powered technologies wave. And there are limitless possibilities for smart systems, and some of them are being already used with success. And while working with current technologies and setting achievable goals, we should still be on the lookout for new and exciting possibilities. With all that, I'd like to thank you all for your attention, and if there are any questions, I'll be glad to answer them now.
All right, we have the first one. Can some HealthTech AI solutions be actually harmful? From Kate.
When implemented poorly, yes, of course. This boils down to the idea I mentioned previously, to focusing not on the metrics itself, but on the actual results they provide. You can develop a system that has, I don't know, like 99.99999% of accuracy, but it achieves that by saying each and every time that the person is healthy. So missing all the suffering people, because the training data set was biased in the healthy person way, because the disease or the pathology is a real improbable one, and the system decides to ignore it. So it all boils down to how it is set up.
We'll give a few seconds for any other questions. Okay, Alex mentioned that you've talked about how to start working with AI solutions by first using simpler models and then developing a bigger system. So could you give an example on how that process will look like? It's also stated in the screen.
All right. I think the natural way to describe that would be on a really simply, a real simple example. So, for example, a startup that is selling something, and they don't have any historical data, any records. So you start with a simple model that predicts the trend, whether their sales will grow or not. And in the background, you start amassing data. And after a few months, maybe you might try to predict how much with a more complicated model. Not using a simple regression, but maybe some more sophisticated tools, ARIMA, SARIMA. Then, when you have that model predicting rough values, you amass more and more data, check the model, and then after a few more months, you may develop a neural net predicting not only how much you will sell, but to whom, or predicting even some, new events that may happen, new trends. So you slowly develop the core, And then you may start by branching out, adding a module that will, for example, try to profile your clients, to predict in advance what will happen. So you add brick by brick and build a big, complex solution.
All right, thanks, Philip. We'll give a few seconds for any other that might come up. Uh, if not, for everyone, for anyone interested, you can also join our newsletters where we are sharing some insights on the recent trends, both in health tech and machine learning trends connected with that. You can find it on our website. Um, I don't see any other questions coming, so we promise to keep it in time. So thank you for attending.
Thank
Um,
you.
great to great to visit. I mean to talk with you all again, and see you soon on the next webinar from that series.